Welcome back, Marauders. This is video 9.3, Gibbs free energy and thermodynamic favorability. So we've learned recently about enthalpy and entropy. Enthalpy is the heat released or absorbed by a reaction, and then entropy is the disorder. Does it become more disordered or less disordered as the reaction proceeds? And in this section, we're going to put those two things together, enthalpy and entropy, put them together into one concept called Gibbs free energy. And the reason we do that is because the enthalpy and entropy change of a reaction will determine if the reaction proceeds in the forward direction under certain conditions. And so we put those together into a concept called Gibbs free energy, and it combines enthalpy and entropy. And then it's going to help us to determine if a reaction will be thermodynamically favored under those conditions. So at a particular temperature, will a reaction proceed in the forward direction, or if it doesn't, it'll proceed in the reverse direction. So the most important equation in this section is this one. So Gibbs free energy at standard conditions is equal to the enthalpy change minus the temperature times the entropy change. The temperature needs to be in degrees Kelvin, and the degree signs here mean that it's at standard conditions. And so standard conditions are going to be concentration of 1 molar for all solutions. And then for any gases, they'd be at a partial pressure of 1 atm. And so we'll calculate that. The enthalpy and entropy we'll put in here. We'll get delta G, Gibbs free energy change. And you're going to look at the sign of it. And if it's negative, the reaction will proceed in the forward direction. And if it's positive, then the reverse would be true, and it would go in the reverse direction. So you want to plug in delta H, delta S, find out what delta G is, and that tells us will the reaction go forward or reverse. All right, so here is an example. We're going to look at the reaction of water as a solid turning into water as a liquid. And so we've looked up the values of the entropy, which is 22.1 joules per degree Kelvin per mole, and the enthalpy, which is 6,030 joules per mole. And so the question, will this reaction occur at 10 degrees Celsius? Will this reaction proceed at 10 degrees Celsius? And so to do that, to figure that out, we're going to calculate delta G, the Gibbs free energy change for the reaction. And so that's going to be equal to the enthalpy change. So that is 6,030 joules per mole, minus the temperature. So the temperature is 10 degrees Celsius. We'll add 273, and you'll get 283 Kelvin. And so times 283 Kelvin. And then delta S is 22.1 joules per degree Kelvin mole. And when we multiply these together and then subtract it from this number, we get delta G is equal to negative 224 joules per mole. This time this was in joules, this was also in joules, so you could just subtract them. Frequently though, this will be in kilojoules, so make sure you make them both into the same unit before you try to subtract. And so this is delta G for this reaction at 10 degrees Celsius. We found out that it's negative, and that tells us that it will proceed in the forward direction. And that makes sense because we are familiar with this reaction. Solid ice turning into liquid water at 10 degrees Celsius, we all know that that reaction will take place. But this reaction doesn't always take place. Ice doesn't always melt. Will ice melt if it's negative 10 degrees Celsius? Well, let's do the calculation again and find out. So same calculation to find delta G, same delta H and same delta S. In most of our problems, we'll assume that enthalpy and entropy don't change very much with temperature. That's an assumption that'll tell us to make in most of our questions. So this will still be 6,030 joules per mole minus, now we have a different temperature, negative 10 degrees Celsius, so that's 263 Kelvin. So lower temperature, 263 Kelvin. And then we'll multiply that times the same entropy change, 22.1 joules over degrees Kelvin moles. And when we calculate that, we get delta G equaling positive 218 joules per mole. And so we find out from delta G here that since it's positive, the reaction's not spontaneous in the forward direction. And when it's not spontaneous in the forward direction, it's going to be spontaneous in the reverse direction. And we know that to be true, that if you're at negative 10 degrees Celsius, liquid water will change into solid water. It'll turn into ice. So if it's not spontaneous in the forward direction, if it's not favored to go forward, it'll be favored to go in the reverse direction. And the negative sign for delta G is telling us it's favored to go forward. The positive sign for delta G tells us the reverse reaction would be favored or would occur. So that was a calculation using this equation where we actually found delta G. Sometimes it'll be useful just to look at the signs of delta H and delta S and use those to determine the sign of delta G and whether a reaction will be thermodynamically favored or not. So in this first example, we have an enthalpy change, delta H, which is negative, and delta S, which is positive. Well, if you have a negative delta H, and then you subtract from that some delta S, which is positive, you know that delta G is always going to be negative. It's always going to be less than 0. That means it'll always be thermodynamically favored in the forward direction. So it'll always be in the forward direction if you have a negative delta H and a positive delta S. Regardless of temperature, it'll always be favored in the forward direction. If you have a delta H, which is positive, and a delta S, which is also positive, then it's going to depend on the temperature. If the temperature is high enough, then this term will be subtracted, making delta G negative. So it could be negative at high temperatures, and it'll be positive at low temperatures. So at high temperatures, a reaction like this, you're subtracting that delta S, and it's going to make delta G negative, so this will be going in the forward direction. And at low temperatures, it'll be going in the reverse direction. If they're both negative, so if they're both negative, delta H is negative, but then this, a negative times a negative, is going to be a positive term. And so this is going to be negative at low temperatures. And so the forward reaction will be proceeding when you're at a low temperature. And then at a higher temperature, it's going to make this positive. So at high temperature, it'll be in the reverse direction. And then our last case, if we have a delta H, which is positive, and a delta S, which is negative, then regardless of the magnitude of these values, regardless of temperature, this is always going to give us a delta G, which is positive. And if delta G is always positive, because this is positive, and then we're doing a negative times negative, so we're adding something to it. If this is always positive, then only the reverse reaction will take place. The forward reaction would never be favored. So it's really useful. A lot of questions that you'll see on tests and quizzes where it gives us the sign of delta H and delta S and asks us to predict the sign of delta G. Or it could give us delta G and delta S and ask us to predict the sign of delta H and so forth. There's another way of calculating the free energy change of a reaction, and that's using standard Gibbs free energy changes. So if you're using the free energy of formation of the products and the standard free energy of formation of the reactants, you can take their difference and find the free energy change of the reaction overall. So it's a really similar reaction to what we had with delta H and delta S. This equation's on your periodic table. You use it pretty much the same as the delta S and delta H reactions that we've already gone over. And so standard free energy of formation for any element in its standard state is 0. All right, so here we have an equation. We want to find delta G for it. And we're first going to do that using the equation that we just looked at. So delta G is equal to, of the reaction is equal to delta G, sum of delta G of formation of your products, minus the sum of the delta G of formation of your reactants. And so using these values, delta G is equal to the Gibbs free energy of formation of your products. So my product was just 2 moles of NH3. So NH3, this value right here, 2 moles times negative 16.7 kilojoules per mole. And then minus the enthalpy of formation of my reactants. And so my reactants are nitrogen and hydrogen. Since both of those are elements in their standard state, they're both 0, so minus 0. And then we find delta G, and it comes out to be negative 33.4 kilojoules. So that tells us that this reaction will be spontaneous in the forward direction. It will proceed in the forward direction because delta G was negative. It'll proceed forward under those conditions, under standard conditions. We're going to find delta G one other way. So the equation that we looked at earlier, delta G is equal to delta H minus T delta S. Sometimes we don't have these values, and so we might need to use delta H and delta S in order to find it using this equation. So we'll go over how to find that. We should see if we get the same answer. We should. So delta H, we can calculate that first for the reaction. So we could take the sum of the enthalpies of formation of your products. So that'd be 2 times 2 moles times the negative 46.2 kilojoules per mole. And then minus the enthalpies of formation of your reactants, which those are enthalpies of formation, they both are 0. And so we get a delta H that's equal to negative 92.4 kilojoules. And we'll do the same thing over here for delta S. So delta S, the sum of the entropies, standard molar entropies of your products. So it'd be 2 times the 192.5. And then minus the sum of the entropies of your reactants. And those are not going to be 0. Notice that these are not 0 even though they're elements in their standard state. So it'd be 191.5 for your nitrogen plus 3 times 130.5 for our, or 130.6 for our hydrogens. And so we'll do that, and we get delta S is equal to negative 198.3. That'll be joules per degree Kelvin. So we've calculated delta H and delta S. And if we have delta H and delta S, we can plug it into this equation to find delta G. So delta G is equal to delta H, negative 92.4 kilojoules, minus T. We're at the standard temperature, so 298 degrees Kelvin, times negative 198.3 joules per degree Kelvin. So the degrees Kelvin will cancel out. This will be in joules. Before you can add this part, you need to make sure the units are the same. So change this to kilojoules. And when you do that and take the difference between those, you get negative 33.4 kilojoules, which is good because that's the exact same thing that we found using this method. So 2 different ways to find delta G. You can find it with the Gibbs energy of formation of your products minus the Gibbs energy of formation of your reactants. Or if you're given or can find the enthalpy and entropy change, then you can use those with this equation to find delta G. It should come out to be the same either way. They both give us the same value. It just depends upon what information is given to us in the problem.